Hello, linear algebra student. This video is for chapter 4.3, part 2. We continue in with checking if a set is a basis for Rn, and particularly R3. So in the first one, we have three vectors, and we reduce row echelon it into the identity matrix. So by IMT inverse matrix theorem, so condition E and H guarantee that it's linear independence and also guarantee that it's span out 3. So it is a basis because these are the two definitions of a basis. What about if I have two vectors? Can it span out 3? Can these two vectors be so good, so efficient that any combination of them will somehow cover all of our 3? Right? So is it possible? So if it does, so it would means my A would equal to the column vector 1, 2, -3, -4, -5, -6. Let's check. Oh well, okay. Let's check if they're linear independent first. If they are not linear independent, there's no way. Really easy to check if because it's two vectors. I only need to check if they're multiples, not multiple of each other, right? So they must be independent. Now, whether it will span out 3, right? We would look at a theorem 4. Theorem 4 is very important in chapter 1. Theorem 4 here say what? Let A be an M times N matrix. In our case, it's 3 times 2 matrix. And we want to know if it span out 3. Only if what? A has a prefix position in every row. It's not possible, right? Our number of matrix is 2. 2 is less than 3 row, so cannot have. So please do not use IMT. Yeah, I should say cannot be Rm by theorem 4, chapter 1, theorem 4 in chapter 1. So cannot have prefix position in all rows, so cannot. Because it only have 2 columns, so the best it can have is 2 prefix position, so cannot span out 3. So although they are linear independent, it's not a basis for out 3. It may be a basis for things that it span, but not a basis for out 3. So you can see that for it to be a basis, at least you have to have 3 vector. But okay, so I have another one. I have 3 vectors now. Can this 3 vector for a basis for R3? So we say, oh, because we have 3 vectors and we are doing R3, I can use IMT. So make the matrix 3, 0, -6, -4, 1, 7, -7, 1, 13, and do the row echelon. Reduce row echelon, see if it is equivalent to the identity matrix. So I think I have inputted. Move it over a little bit. 306, 41 negative, 306, 41 negative, 417, -7, 113 is this one. So row reduce echelon B. Oh, it is not. It's 10, -1011, 1000. So it's not reduce row echelon 1011, 001, 01, 011. Oh, there's no and 000. What? 011. Yeah, 011. So it is not the identity matrix, not I3. So because it's not a row reduced echelon to I3, so it is not independent. We can tell that they are not independent. As a matter of fact, you can tell that the third one is a linear combination of this first two. They're not independent, so also not span out 3. So IMT is very good if you have 3 vector. What about if I have 4? Okay, you cannot skip n. Maybe I'll give you one more. So I would have a new matrix of 3, 0, -6, -4, 1, -1, 7, 1, 13, but one more, which is 4, 1, -2. Would this be linear independence? No, it cannot be because the first three is not linear independent. This would not be linear independent because I have 4 vectors and is greater than 3. And actually, we know that they are. One of them is a linear combination of the other, so they must not linear independence. Now, you cannot use IMT here. Not linear. One of them, just like the first 3, is the linear combination of the other. So it's not a basis. We don't even have to check the prefix columns or anything because it will not be. Did I do it? No, I don't need to do it, right? Because if they are not linear independent, they cannot be a basis. Now check 1t squared is a basis for P2. Did I did that already? In my first video, did I check that 1t squared is a we checked that they are linear independent, right? So we don't know if it span out P2. Can it span P2? So refer to example 2 above in page 1. So this set 1t squares are linearly independent. So can it span? Then we can actually say, so that means span means whatever that it's, if I have a matrix, I have a polynomial, let let P equal to, say, A0 plus A1t plus A2t squared. Can I write it as a linear combination of this? Yes, because this other way you write a like a any polynomial of second degree. So by inspection, it is, right? So there is not another way to write it, and this is it can be any polynomial of degree 2. And I cannot make it a little smaller. I cannot take away t squared because then I would not have t squared. So this this is a basis. As a matter of fact, it's a standard base. So we have the next one. Instead of looking at Rn like R3, what about I have a set V1, V2, Vp, and I would have a subspace that span it. I just do the linear combination of all of them. It would be a subspace by 4.1 said that if it is a vectors in V, yeah, is a set and you span it, the spanning is a subspace. So can I find the basis? Can I find the basis for this H? So would it be can I select vectors to form my basis? So what we do is this theorem guarantee that the basis must be inside the spanning sets. Okay, so this may be too much, but the basis will be inside it. First of all, so if H is not 0, then a subset of S is a basis for H. So you pick some, and then you can say you can remove those that are a linear combination of the remaining one. Then the remaining set would be a basis. That means you cannot have a basis that is outside of these spanning sets, right? Okay. Let's say we have 3 vectors and we want to find the spanning set for these 3. So if they are linear independent, I think that would be true. This would be a basis. So let's see if they are linear combinations. So first, the idea for the spanning set theorem is to find a basis in a spanning set. You would just pick them, discard the vectors that are linear combination of the other. So figure out which one is a linear combination of the other, or if they are linear independent. If they are linear independent, this is already a basis. So let's see. I'm just going to make them A equal to 3, 0, -6, -4. To see if they are linear combination of the others, what you can do is solve for 0, 0, 0, right? So solve for if there's ways to make them 0. So let me solve the homogeneous system. So I have this 7, no, -2, -215, 30, -6. Yeah, 4100. So I need to get one more column, which is 0, 0, 0. So to see, and then, oh, this is B, right? B, oh, oh no, this is not the what I'm looking on. -215. What? I'm confused. -215. I only want -215, right? 30, -6, -417, -215, 0, 0, 0. So this augmented matrix. So, oh, so actually I would have to solve A 0, -6, -417, -215, x1, x2, x3 equal to 0 has a solution. So that means this is not A, this is actually the augmented matrix, so don't mix up. And so this augmented matrix, if I do the row echelon form, is 1 0 0 0 1 0 0 0 1 0 0 0. So it is the only trivial solution, right? So these are the bases for the span. So V1, V2, V3, I don't have to discard anything, is the basis for H, which is the span of them. So you don't have to like go out and invent another set. The spanning set, if you discard all those that are linear combination, is already. Let's do the one that is 1, 2, 3, 4, 5. I have 5 vector, right? So I want to find the basis that's spanned by this. So that means if I do span of these 5 vectors, V1 to V5. So what is one of them that can what is the smallest one that I can smallest set of these vectors that can actually equal to the span, right? Is there anyone that is redundant? So I will need to solve for a x. So let's this be a, right? Write this in a x equal to 0 again, because I want to see if they're redundant. Oh, here, this one. 1 0 0 1, right? -2 1, -2 1, 6 1, -2, 0 3, -1 1. I want to do a column of 0 0 0 because this is see if they are linear dependent of each other. So and then I do reduce row echelon of D. Oh, not E, D. So it become, oh, I only have 3 pivot position. Right? 3 pivot position. All these are free variables. Free variables. So the augmented matrix is row equivalent to 1 0 0, -1 -2 0, 0 1. So I don't think I can finish it. I'll continue in the next video.